In this section, we are going to talk about seafloor spreading. There's a couple really awesome tools that scientists use to map the seafloor. One is a magnetometer, and that is a device that can detect small changes in magnetic fields on underwater. And here's a cool picture of it. And then another one that is used is sonar technology. Boats will float along and send down basically sound waves to map the floor of the ocean. That both of these are very intensive, like takes a long time and expensive process to do, but it is done over time by various scientists that are out in the field. So what scientists have found is that there are various ocean ridges along the ocean floor, and a number of them are mapped here, different ridges. And there are also some trenches, some places where it goes very, very deep. And the deepest trench that we know of is this Marianas Trench, and it is so deep that you could put Mount Everest in it and stack many Eiffel Towers or Empire State Buildings on top of that, and it still would fit it. So it's a very, very, very deep trench. So what made all of these underwater mountains and valleys? That's what we are going to talk about with seafloor spreading. So in the seafloor, you will often find these ridges, these high spots, and you will also find these trenches with low spots. And seafloor spreading is the actual process that makes new ocean. In oceans, ocean rocks are actually younger than continental rocks. So rocks in the ocean are actually younger than what we have up on continents. Additionally, what we have on land up on the continents is much thicker than what we see in the ocean. Inside of the earth, at the core of the earth, you have the iron, the molten iron at the core of the earth actually will flow in a current. And right now, it's flowing in this motion with magnetic north being at the North Pole. We call this a normal magnetic field. And then the reversed would be to have the north pointed towards the South Pole, and the current would be going downward. But right now, we have this in the normal magnetic field going this way. Well, what does that matter? Because this has reversed itself over time. And what does that matter? Well, here we can see that rocks that came out of let me see if I can move to this picture. As the molten lava comes up, there will be some rock particles that are magnetized. There are some with metals in them that are magnetic. And when that lava is molten, it can still move. So the magnetic portions will face the current North Pole. And if the current North Pole is at the North Pole, then they will face that direction. And then as they freeze, they will stay, cool down, they will stay frozen facing the North Pole. So as this lava comes out right now, it will cool down all facing the North Pole. Well, a long time ago, though, at other points in our history, this, like in these orange sections here, when the lava was coming out, it would kind of cool down and freeze in time, not actually freeze, but it would cool off and be stuck in that position facing the South Pole. And at other points, it was back up facing the North Pole. And then at other times, it was back facing the South Pole. And here we have a whole record of rocks that are facing different directions based on the poles at the time. So as you can see, we are here in this red, which we call the normal version, but you can see that most of the time we had reversed polarities. So most of it's actually orange. So it's actually less normal what we have right now to have the polarity switched. So what does that have to do with seafloor spreading? Well, it's interesting because as the lava comes out and it spreads to both sides, one side will actually match the striations or like the different um, magnets on the other sides. They will actually mirror each other. So here you match on this right side, you'll match this left side, and then this right side matches this left side. All the way down, they will have their matches going all the way across. Um, so an isochron is a map. I want to show you that here. That actually it's just a line that's drawn by people that are looking at the maps that will show the same points on a map that are the same age. So the younger Earth will be near the ridges where new land is being formed and created and coming out of the spreading joints. And the older land will be near the trenches or near the outsides. Something I want to point out here that's really interesting, if you look at the band in the Pacific, so this is where we are, and we know we have the Pacific Ocean, right? You'll look at how wide our red younger bands are versus this much tighter red band. Well, what does that show us? That actually shows us that the Pacific is spreading very rapidly. This young land is spreading out really fast, whereas down in the Atlantic it's much slower. Interestingly, this Pacific is spreading here at about 8 centimeters a year, and that's about just over 3 inches. So over 100 years, say you get to live 100 years, this will actually spread right here by about 26 feet. That's a great distance to have that spread over 100 years, which is not very long when you think about the age of the Earth. So again, here's a cool picture of seafloor spreading. So seafloor spreading acts like a conveyor belt where magma will come up here at a ridge and make a volcano and burst out a lot of lava, and that cools off facing, north or south, and then and each side will match and it will spread out, and it'll spread to a point where it hits something else, like something that's cooler, and it will subduct and go down. And then basically it'll get so much pressure and heat that it will melt again and come back up, or it can even go off to the side and make volcanoes and explosions over here. So it acts like a conveyor belt in that it spins around and it circles around and around. So evidence of seafloor spreading are that um, rocks on both sides of the ridge match in their age and in their thickness. Also, there are younger rocks near the ridges and older rocks near the trenches, which is what you would expect. So common seafloor, ocean floor features are ridges and trenches. And most of the ocean is actually, even though this is young lava rock here, on top of it is a giant thick layer of actual just sediment that falls down through the ocean. So while this is lava rock here, this is almost sedimentary rock, but it's not that hard usually. It's just sediment, dead things that have died, garbage, different particles in the water will all settle on top of this to dig down before you can get to this harder layer. So that's seafloor spreading, and we'll move on to our next topic.